Hello everyone, welcome to our Assistive Robotics presentation. This is our group. First, Aditya will start by introducing the hair model elements.
The elements of the hair model for the assistive task implemented are as follows. The human subject under consideration is Ron. Ron is rapidly losing his hearing and has cataract in one of his eyes. He has trouble having conversations with people, especially in the presence of background noise. He has restricted mobility because of his arthritis and had undergone a hip surgery in the past. He might have reduced reaction time due to a decrease in motor function caused by his arthritis condition, and he might also be experiencing fatigue frequently. His situational awareness should be normal. The assistive task is to help and guide Ron to perform seated exercises to increase mobility of his hips and circulation. It can be considered as a relatively less complex task. There is considerable amount of collaboration with Ron during the task. Expected duration of the task is around 9 minutes. The robot would at least be an arm's length away from Ron to avoid the risk of collision. The robot would mainly rely on verbal conversations with Ron to perceive his status. The robot to be used for the assistive task is Pepper. Pepper is programmed to be fully autonomous throughout the task. It can display information through the monitor on its chest and can also speak and understand verbal cues. It can move around and can manipulate its arms and its head based on how it is programmed. Users can mainly interact with Pepper through speech and by using the touchscreen on the display. Pepper can last 7 to 20 hours on its battery. It can be accessed through either Wi-Fi or an Ethernet cable. Pepper also has a number of sensors including ultrasound, sonar, laser, gyro sensor, etc. The environment where the task would take place will be Ron's home. Since it is a house, moderate lighting and limited background noise can be expected. Precise locomotion of the robot might be required if the house is small or cluttered. External disturbances are expected to be minimal in a house.
As Aditya has introduced the hair model in context with the HRI interaction that is happening in the experiment, now with the disabilities of Ron taken into consideration and the routine of the physical exercises that Ron needs to do with Pepper in order to take care of his physical health, I could like to explain the brief overview of the flowchart of the human-robot interaction that takes place in this experiment. The flowchart is divided into 4 segments: the introduction phase, exercise routine phase, entertainment activities phase, and a closeout phase. Let's move to the introduction phase. In this phase, Pepper will try to find Ron using its tracking ability, and as he is losing his ability to hear, it must approach him with a louder tone so that Ron can hear Pepper's voice, which grabs his attention. After finding Ron, Pepper will do a well-being check, which is it asks him questions about his day, family, and his social interaction with his friends.
First, some quick questions for the doctor. Will you still have time?
After that interaction, it moves to the exercise routine. In the exercise routine phase, Pepper provides step-by-step instructions based on the scripted program written by us.
Now, we will try some chest stretches. Look at the picture. Sit upright and away from the back of the chair. Pull your arms back and down. Extend your arms out to the side like me.
In this experiment, we have considered Ron's situation of hearing problems and cataract in one eye. So to help him better, we have provided him with more interactive ways like displaying the exercises steps on the tablet and in the form of audio-based effects like counter sounds, like small beeps for the counts of the exercises along with Pepper's voice for the instruction. And the exercises were designed from the NHS website with the hip surgery and arthritis taken into consideration. We have made most of the exercises in the seated postures. In between the exercises, Ron must be relaxed and motivated, so we have added the entertainment phase in between the exercises, which we will see in the next slide. The entertainment phase was designed to make him relax during the exercises by playing his favorite music to hear or a joke to entertain him and make him happy.
Do you want to listen to music?
Yes.
I can play your favorite.
We also added some of the voice messages from his friends, which we also tried out during the roleplay with Pepper, that motivates him to make social interaction with others.
Oh, I have a message from your friend Wayland.
Hi Ron, haven't seen you in a bit. I'm Wayman.
This phase runs in between each exercises as a decision loop. If Ron feels tired between the exercises, if he says no to a next exercise, then the loop from the exercise will switch to the entertainment phase, which contains the things that I just mentioned. This break is mostly for 30 seconds. After that, it moves back to the exercise routine phase. After the exercises are completed, as recommended for the day, the pepper appreciates Ron for performing the exercises with good amount of enthusiasm, and the interaction comes to an end with a goodbye note.
Good job on exercising today. You did better than the last time. Let's exercise more next time. See you soon. Bye.
This is the limitation part of the Pepper platform, which will be introduced by Wayman and I. We summarize these limitations from the process of doing the task. The first limitation is degrees of freedom. Because of exterior design of Pepper has fewer design degrees of freedom than humans have. So he can't twist his body, can't raise her legs up, and so on. As a result, for some exercise action, like the picture shown, we display images on the tablet for Run to follow, which may be not vivid. And Pepper can't do this action with Run together, so it lacks interaction and seems boring. The second limitation is the external detection. When coding, we want to know whether Ron has finished the action, so we can decide whether Pepper can do next exercise action. Even though Pepper has cameras and in-flight, posture of detection is hard, especially there is no functions about posture detection in Pepper's build. If we use the external library, it's hard to carry it to Pepper. If we train it by ourselves with machine learning, we need to lots of images and also it is time consuming. Last but not least, the algorithm of that is difficult. Following limitations will be introduced by Wayman.
Thank you, Wenchao. Speech recognition accounted for some of the limitations that we encountered during this project. For instance, if Ron were speaking to Pepper right now, the Pepper robot may need to take some time to understand what Ron is trying to say. The recognition accuracy isn't always 100%. A person may need to change his tone of voice or take multiple tries to get through to the robot. We cannot have duplex communication either, because either the human needs to finish speaking first, or the robot needs to finish speaking before the other can proceed. If someone has an accent, the robot may struggle to understand that person. And lastly, if a person speaks a language that is not supported by the robot, we may need to use an external library to allow Pepper to understand what this person is trying to say. When it came to interactions between Pepper and Ron, we only programmed the Pepper to give Ron exercise instructions throughout the day. So if Ron were to ever refuse or decline suggestions to exercise from Pepper, then Pepper has no course of action to take. The dialogue are pre-programmed into Pepper, meaning that Ron must say something that Pepper expects him to say. He cannot say something out of the blue because Pepper will not understand him. Unfortunately, if Ron were to ever power off the Pepper, then the Pepper has no way to recover. It would just stay powered off. And as a worst case scenario, if Ron were to ever run away from Pepper, then we have not programmed the Pepper to chase after Ron. Getting code to run on Pepper also had its own set of challenges. Out of our 5 team members, we only had one Pepper robot to share. Therefore, we dedicated one person to hold on to a master copy of our code that was used on Pepper. If one person were to add a new exercise on his own separate choreograph instance, his changes needed to be copied over to the master copy and then uploaded to Pepper. If this process was done incorrectly, say if a programmer had a different version of choreograph, then we encountered issues like broken timelines or update loops. Sometimes even choreograph would crash if there were inconsistencies. I'm going to hand it over to Emmanuel now, who's going to present on recommendations and future works.
All right, now we move on to recommendations and future works. We would like to place special emphasis on the following: user-centered design, which we believe to be the key for a successful assistive robotic system. Right now, we're missing the key area of evaluation. The testers in the system are not representative of this final sample of people that act or behave like Ron. We are relatively fit, we are savvy with technology, and we already know the exercise a priori, which is a significant major limitation. For a successful system, we need to go through several iterations of this user-centered design process, test frequently, identify problems, and prototype to fix this. Moving on to more concrete proposals to solve other problems. First, we have sensing. One of the key limitations is that currently the Pepper cannot sense the user, and we would like to implement that. This can be accomplished by different machine vision techniques to find the body position. And with this, we could offer not only real-time feedback, but also make recommendations at the moment and in the future to the user, or use data from the past. And we could collect this data into packages and actually send it to medical professionals. Implemented, this is not completely straightforward, but there's evidence of this being done in the past. Here is done with NOWS, which is a similar backend to the Pepper. However, these solutions are not completely straightforward, as we will need to require to train a model with pictures of people that look like that fit Ron's model. And it has an interesting limitation in that the camera is usually mounted on the Pepper's head and it moves during exercise. There's options to circumvent this, for example, using an external camera. In this case, for this example, somebody used a 3D camera and successfully achieve body segmentation and accurate description. And implementing an external camera has other advantages, like allowing the Pepper to find Ron in different parts of the group, covering for different lifespans. We also believe that implementing a diverse system of biosensors could significantly improve performance. We could not only track heartbeat, body temperature, sweat, and save all of this into a package with the rest of the data. It's further amplifying the data we have. Moving on to exercise demonstrations. Right now, we would like to implement video activities, which I believe to be self-explanatory. Right now, we're using images. We'd like to move into videos. These are currently supported by Pepper, and we'll only need to actually create the videos. A feature we like right now particularly is our ability to show progress by simply overlaying an image. We would like to clean up the code for this, offering a programmatic solution rather than simply overlaying a number on multiple images. And in the same way that we're showing a roadmap of sorts by numbering the images, we would like to offer a roadmap for the total activities presented during, before, and after the overall workout. We believe this will give the user a more clear vision of the start and end goal of their activities. And now, moving on to actual interaction, we recognize significant problems with the speech. And this could be, there are different strategies to mitigate this. We could, for one, implement more complex dialogue trees, but this is not infinitely scalable. We would leave the long-term successful strategy to be implementing a sort of semantic analysis, and there's Python libraries that could be used for this. On a short term, however, implementing other means of input, like body gestures, nodding for example, or facial expressions to get even more data. And finally, we move on to development improvements, and in which correspond mostly to quality of life. One of these will be implement better collaboration features. For example, automatic automation commits will significantly speed up development. Adding features like integration with popular home assistants like Alexa, Google Now, stuff like that. And adding this crossing of ecosystems will significantly improve the amount of features available, as right now we're implementing stuff like we're simulating calls and messages or implementing random weights rather than outright using them. And general stabilities to the code that could be done user side by optimizing our code, or the base program side by simply updating versions or fixing backend. And with this, we're done with our presentation. Thank you very much for your attention throughout.